Assalamu alaikum. Welcome back to Medical Physics MTPT webinar series. And we will continue our webinar from yesterday where we left. For the participants who joined today, I will add a short and brief introduction about myself and the speaker. My name is Syed Jawad Ali Shah. I am currently working as senior medical physicist at Ednam Cancer Hospital, Peshawar. Our speaker for today's webinar is Muhammad Ali Shah Saab. Muhammad Ali Shah Saab is a chief medical physicist, one in St. Luke Hospital, Iowa, and other is Finley Hospital, Iowa. Our topic of the webinar is radiobiology. Yesterday, we discussed a few concepts of radiobiology, gap calculation, decay calculation, and today we will continue from the yesterday where we left. Muhammad Ali Shah Sahab, you can continue, sir.
Assalamu alaikum, everyone. So yesterday, what my intention was to start with the calculations and then go on and build our concepts. And once we grab those basic concepts, we will go 360 degrees around and go back to our initial discussion of the calculations. Yesterday, during our discussion, we briefly touched the 4 R's of radiobiology. During our fractionation schemes, when we do the conventional fractionation, the 4 R's are very important. Those 4 R's are repair. So once we radiate the patient, let's say we radiate the patient today, and we are treating the patient 24 hours later, what's happening in the cells during those 24 hours is the cells are trying to repair themselves. So as we discussed, the phase division phase, gap 1, synthesis phase, and gap 2, the cells are trying to repair their damage. They are looking and self-analyzing and trying to repair anything that was lost. The second is redistributions. So during those 24 hours or 6 hours, sometime we are treating after every 6 hours during a day, the cells are redistributing themselves. That means they are going from phase one to synthesis, or synthesis to G2, or G2 to M. So they are changing in those phases, and when cells are doing that, that process is called redistribution. And if you guys remember, we also talked about the time for each phase. So when the cells are taking some, for example, during division, the cell is taking 1 hour, and after that hour, the cell will be in G1 phase. Similarly, when we were hitting the cells during radiation treatment, and out of those billions of cells, they were in different phases. The next day, they will have changed their phase. So some of them will be in S phase, and some of them will be in G2 phase. So some cells that were in S phase during the first radiation may have moved to late G2 phase, and it will be a good time to hit them. So as one of the students asked yesterday, or one of the participants, sorry, one of the participants asked, how do we know about the phases of cells when we are radiating? So actually, when we are fractionating, we are letting cells to change their phase and get into our ideal phase when we are treating. Repopulation. And after the treatment, when the patient goes home, the cells that are in M phase are dividing. So the cells are repopulating as well during our gap. And reoxygenation. Reoxygenation is another very important aspect. If we think of tumor, as the tumor grows, the center of the tumor get less and less oxygen. When the tumor is deprived of oxygen, the tumor cells that are in the center, when they are deprived of oxygen, they become radio resistant as well. Their response to radiation decreases. So when we are treating a tumor, the outer cells have more response to radiation because they have more oxygen, and the the innermost cells have less or no oxygen, so their response is very small. So when we are treating, we are kind of peeling off the outer layers day by day, and we are getting into the inner side of the tumor, and those cells are getting more and more oxygen with the passage of time when we are treating the tumor. So during the time phase when the patient is at home, or we are not treating the patient, these processes are happening, and these processings can be friendly to us or can be non-friendly to us depending on where we are looking at. So these 4 R's of radiobiology are very important when we talk of fractionation scheme. So repair between fractions should be complete for normal cells. So the normal cells that we hit, we want them to be completely repaired when the patient come back. And at the same time, we want the tumorous cells to, to maintain that damage that we did a day before. In general, time between fractions for most tissues should be greater than 6 hours. We should not treat before 6 hours, because then we are harming the normal cells more. We will be doing damage to the cancerous tissues, but we will be harming the normal cells more. And the second thing is, from our just discussion of the R's, the cells, most of the cells or some of the cells may still be in the same phase. They may not have changed their phase. So when we treat before 6 hours, that may be not of any use. Some tissues like central nervous system or CNS recover slowly. So for those, BID treatment is inadvisable, because there will be no use of a BID treatment as the cells are recovering very slowly. And we are talking about normal cells here. In acute responding tissues, tissues that respond quickly, regeneration repair has a considerable sparing effect. So remember, when we are treating with radiation, we talk of sparing effect for normal cells. That's why we, like in the past, in the good old days of before MLCs, we would have a box treatment for prostate, and we would go for more and more gantry angles in order to spare normal tissue and get the tumor from all the sides and give it the full dose. So in acute responding tissues, repair has a considerable sparing effect, and prolonging treatment time has a sparing effect, but we cannot prolong it to the point where the tumors start recovering. In late responding tissues, prolonging overall treatment time beyond 6 weeks has a little effect. But that means if we are treating every day and we reach up to 6 weeks for late responding tissues, delaying it, like prolonging our treatment for more than 6 weeks, has little effect. But prolonging time to retreatment may increase tissue tolerance. That means retreatment means if we decide that we are treating instead of every day, we are treating every other day. So that is the retreatment, and prolonging that time will increase tissue tolerance. The tissue will become more radio resistant. And types of radiation damage, we talk of lethal damage, which is termed as LD. The lethal damage is irreversible. The chromosomes and DNAs are broken beyond repair. And this irreversible, irreparable damage leads to cell death. You will hear terms like LD50 or LD50/60 or LD50/30. This means when you see something like this, LD50, that means 50% of the cell population has been killed. And if you see a term like this, that means that 50% of the population is killed in 60 days. Sublethal damage. Sublethal damage can be repaired in hours unless additional sublethal damage is added and delivered that eventually leads to lethal damage. So for normal cells, our friend is sublethal damage. When we are treating a patient, we are hoping that we are doing a sublethal damage to normal cells, and at the same time, we are trying to deliver lethal damage to the cancerous cells. Potentially lethal damage can be manipulated by repair when cells are allowed to remain in a non-dividing state. So if the cells are staying in non-dividing state, they are in synthesis state, they can repair themselves And the potentially lethal damage, the damage that had potential to kill the cells. And in case of cancer, we are hoping that the cell will die, but if we prolong the treatment and the cell stays in non-dividing state, by staying in non-dividing state, the cell is repairing itself and is manipulating our potential lethal damage. So in human population, we have somatic effects. Somatic effects are exposed individuals suffer during lifetime. So if someone is exposed, that exposed individual may get the effects while he or she is alive. Examples are radiation induced cancers, sterility, opacification of the eyelids, and life shortening. So these are some examples. There can be others. So anything that happens to the person who got exposed, those effects are called somatic. Then we have genetic or hereditary effects, radiation induced mutations to an individual genes and DNA. So if the genes and DNAs are mutated to an extent that they can transfer to the offsprings, then we can have birth defects in the descendants. And this is an effect of radiation that can be transferred to the next generation. So when we are talking the effects on a person who got exposed, we have stochastic effects where the probability of occurrence of any effect like cancer or something, the probability of occurrence increases with increase in dose. So as the exposure dose increases, the probability of stochastic effects also increases. But severity in affected person does not depend on the dose. So even a small dose can create something like if someone is exposed to a small dose, that can create cancer, like induction of cancer and genetic effects, or sometimes a large dose may not do anything. So in stochastic effects, we are not talking about the amount of dose. Even a small dose can do some harm. And stochastic effects have no threshold dose. So if someone is even exposed to a small dose, stochastic effects can happen. There is a theory, and that's alcohol hormesis theory, where they say that at low doses may be beneficial. But that is a different topic, and I have not touched that in my discussions here. If you get a chance, look at that also. But remember, we don't use that concept in any of cancer treatments as well. So that's why I never touched it here. The second effect is called deterministic. In deterministic effect, this increases in severity with increasing dose. So as the dose increases, the chances of deterministic effects becomes more and more, usually above a threshold dose. So for deterministic effects, we do have a threshold dose below which we hope that nothing will happen, and is caused by damage to a population of cells. So when a population of cells is exposed to radiation, deterministic effects will happen. And as they get exposed to more and more radiation, the chances of deterministic effects become more and more clear. So we can say like organ dysfunction, some organ may stop working, fibrosis. For organ dysfunction, when we are treating head and neck patients, we do talk about those two glands in the mouth. So if we irradiate them below a certain mean level of dose, the patient cannot produce saliva in their mouth. So that is an example of damage to an organ and deterministic effect, because at low doses that will not happen, but as with the passage of treatment, when the doses to those glands are increasing, um, we see that patient complain of no saliva in their mouth. Fibrosis, lens opacification, blood changes, these are different types of deterministic effects. And as stated, there is threshold dose. So below a certain dose, there will be no deterministic effects. So for us radiation workers, we bet on the deterministic effect. When we wear our badges during our work, and those badges are recording our dose, so we are hoping that we are exposed to a level of dose that is not harmful, and that the dose has a threshold effect, and hopefully nothing will happen to us. Remember, we are forgetting about the stochastic effects, those at that time. We are just betting on deterministic effects. So as exposed organs can show response immediately, or the effect may appear at a later stage. So the organ that is exposed, if it's a very high dose, we can see immediate effect. And if you have studied the skin erythema dose in the past, that was the indicator of we would irradiate the skin, and that is very past, almost 100 years ago. We would irradiate skin to a dose when it will become red, and we will say, okay, we have delivered enough dose. So so that will be like exposing some organ to a dose that will, the changes will immediately appear. This immediate effect, also called acute effects, and appear soon after exposure. They appear very quickly. As I said, the reddening of the skin. Some examples are inflammation, edema, denudation of epithelia, and hemopoietic tissue, and hemorrhage. Late effects, also called chronic effects. So we will be using the acute effects and chronic effects. So remember, immediate effects are acute effects, and late effects are chronic effects. So the late effects are delayed. When someone is irradiated, or someone is exposed to a high dose of radiation, the effects will not occur immediately. It can occur after some time. And that the time between the radiation and the occurrence of cancer or occurrence of effects is called latent time, during which nothing happens, and then suddenly the effects of radiation start happening. It can be caused by absorption directly in target tissue, or consequential to acute damage in overlying tissue, such as mucosa or epidermis. So if mucosa or epidermis is irradiated to high doses, the tissues that are adjacent to it may get some side effects. The examples are fibrosis, atrophy, ulceration, stenosis, intestinal obstruction. So atrophy, shrinking of muscle, and stenosis, the narrowing of veins, these are the effects that can happen, and these are acute effects that will happen lately. So when we are treating a patient, and the patient uh, complain about like stiffening of muscles or something in the radiation area, that may be one of the late effect that we are causing. So the response of a person on acute total body irradiation exposure is influenced by the combined response of all organisms. So like in humans, when someone is when a whole body is exposed, then the combined effect of all organisms will show some effect, and that is the acute total body result. This response, a whole body radiation response, is specified as radiation syndrome, and it depends on the acute body dose of above 1 gray. So if someone is exposed, the whole body is exposed to a total dose of above 1 gray. From 1 gray to 10 gray, we can get bone marrow syndrome. From 10 gray to 100 gray, we can get gastrointestinal syndrome. And above 100 gray, it's central nervous system syndrome, and that is death. So if someone is exposed above 100 gray, whole body dose, that is an immediate death. Death can occur from the other syndromes also, but that may be slow and painful death. CNS will be an immediate death. Now we comes to our discussion of cell survival curves. And this is where we talked about equations yesterday also. Um, in cell survival curves, there are two theories. There are a lot of theories, but there are two theories that are kind of favorite of radiobiologists, and I will discuss them here. Um, Remember that there is a book online by IAEA, International Atomic Energy Agency, and that book is available in PDF form. So for those of you who would like to explore more of radiobiology, you can download that book for free. And I have prepared most of my slides from the atomic energy material as well. So like this graph is from one of the atomic energy material. So you have options available online that are for free, and you can download them and read them. So now talking about cell survival curves, a cell survival curve is obtained by plotting surviving fraction against absorbed dose. So this surviving fraction is the fraction of cells that survived a certain level of dose. So we have surviving fraction on y-axis and absorbed dose on x-axis. So as the dose increases, more and more cells are dying. So the surviving fraction, the cells that are remaining alive, is getting less and less. So at low doses, we have more cells present, and as the dose increases, the cell colonies are dying and we are getting less and less cells available. Surviving fraction, denoted by S, is plotted on a logarithmic scale. So as you can see here on y-axis or ordinate of the graph, we have logarithmic scale. And the dose is on the x-axis or abscissa of the graph, and this is a linear scale. So high LET radiation, which are densely ionizing, yields will give a curve that is an exponential function of dose, a straight line on a log linear plot. So you can see this is for high LET. They are highly damaging, and we will get a curve like this. For low LET radiation, um, low LET radiation give us a curve that has an initial slope. We have an initial slope, then we have a shoulder, and then we have a straight line, followed by a shoulder region, which is here, and then becomes straight at higher doses. So low LET radiation that are our X-rays and electrons that we treat our patients with, it gives us some threshold dose. And high LET radiation is just a straight line. They don't give us a threshold dose. And these terms dq and d naught, we will discuss them next. So d1 is the initial slope. Now remember, I will go back to the previous slides here. Um, Here we are, when we talk about the initial slope and the shoulder, we will be talking about low LET radiation, because with the high LET, we are just started killing of the cells. We don't have any initial straight curve, and we don't have any shoulder in high LET. So when we are talking about initial shoulder and D1, basically we are talking about the low LET radiation here. So we have D naught. D naught will be a function of the straight line that is at higher doses, and D1 will be a function of the straight line that is at lower doses. And then we have this shoulder. And then look at this line. When we extrapolate this line back to the surviving fraction line, um, the point where it touches the line becomes our number n, which is called extrapolation number. DQ is the quasi threshold dose. I've heard some people calling it Qazi as well. Qazi is some a respected family in Pakistan. So quasi threshold dose or quasi threshold dose, whichever way you like. So D1 is the initial slope, mathematically the reciprocal of the initial slope. So when we take the reciprocal of the initial slope, that is the D1, which is the dose required to reduce the population of cells to 37% of their previous value. Remember, this will be reducing to 37% of their previous value. So if we have 100 cells present and we deliver them a dose of D1, their population will reduce to 37%. And so now we have 37 cells, and when we irradiate 37 cells with dose of D1, again these 37 cells will go down to their 37%, which will be 13.69. So D1 is a dose, and D naught, they reduce the population of the cells to 37% of their previous value. And D1 is the initial state portion of the curve, And again, this is a very important point here. Please remember this. D1 is due to single event killing. So single event killing, remember we discussed yesterday about single strand break and double strand break. When we do a double strand break, we just kill the DNA, or we just kill the chromosome right there. So that will be a single event killing when we break both the strands, and the DNA or the chromosome cannot repair itself, and the DNA cannot repair itself, and they are broken. And then during the division, when they try to divide, they check their integrity, and then apoptosis happen. The cell kills itself because the cell think that it's not good to divide. Coming to D naught, which is the final slope of our curve. If you can see this curve in the background, I'm talking about the final line for D naught. This is the final slope. So again, this is the slope of the line, but this is the slope of the line that is after the curve, after the shoulder. And it does the same, reduces the population to 37%. Now, D naught is due to multiple event killing. That means we broke the strands in different areas, at different locations. But what happened was that breaking of the strand made chromosome unable to repair itself, or when it repaired itself, something happened, and it repaired itself abnormally, and now cannot carry on, cannot go to division phase, or when it try to divide, it just dies because now it's abnormal, and that is called chromosomal aberration. We will touch this shortly also. So due to multiple event killing, when we hit DNA in different places, we do not hit both the strands together. We do not hit it with single uh, ionization event, but we hit it at multiple times. And when it is trying to repair itself, it does not repair itself correctly, and it dies from that. So any cell killing that is happening from multiple events killing, that is called D naught. And DQ, the quasi threshold dose, and we think that below this dose there will be no effect. So in the slope you can see that we have a initial line and then a slope. So below this dose there will be no effect. Actually, there is no dose, there is no threshold dose below which there is no effect. So that's why we call it quasi threshold dose. And the term quasi is taken from the movie Hunchback of Notre Dame. And in Hunchback of Notre Dame, when the deformed kid is handed over to a priest in the church, the priest says that this kid is quasimodo, like he is not a full man or a complete human, but he is almost a person. So quasi means in Italian for almost a person. So this is almost a threshold dose. This is not a real threshold dose, but we hope that this is a threshold dose, and the normal cells will repair themselves, and the cancerous cells will stay in the damaged state when we look at them next time. And N, as I discussed earlier also, its extrapolation number, N is a measure of the width of the shoulder. So if N is large, say 10 to 12, the survival curve has a broad shoulder. If N is small, 1.5 to 2, the survival curve has a very narrow shoulder. And, and as I said, it is the point of intersection of the slope on the log survival axis. So when we extrapolate back the line, when it goes and hits the survival fraction line, that is the point which will be N. Mathematically, N is equal to, log of N is equal to dq by d1, d naught. Yeah, I had it written here. Log of N is equal to dq by d naught. So dq, which will be our threshold dose, we can find dq by multiplying d naught with log of N. So that is one model. When we discuss the threshold dose, and we discuss d naught and d1, and we look at log of N, and we look at a threshold dose for a certain tumor or a certain organ. We look at a threshold dose, and then we try to treat up to the threshold dose, so that the normal cells don't die and the cancerous cell is damaged. So the normal cells repair themselves better than the cancerous cells. So the next day when the patient come back, normal cells are repaired and the cancerous cells are still damaged. The second model, which is very popular, is the linear quadratic model. And linear quadratic model is very popular in our field, and we use this model most of the time. And this will take back us to our equation that we discussed yesterday. The equation for linear quadratic model, survival fractionation is equal to the exponential of alpha d and beta d square. The 2 is in power for d. So now the concepts of alpha and beta are here. But before discussing alpha and beta, I talked about chromosome aberrations, and I said that the chromosomes may have been damaged with multiple hits to an extent that they cannot repair themselves. So what may have happened is, we let's say there is a red chromosomes will be the same, but in order to distinguish between them, let's say we have one chromosome and another chromosome, we hit them. It was a this is a double hit. We hit one chromosome here and the other one here. So theoretically we did not hit both the strands, and we did not kill them with a single event. We have hit two different chromosomes, but when they were trying to repair themselves, somehow the portion of this chromosome got attached here, and the broken portion of this chromosome got attached here. So now when these cells go and when they try to divide themselves in mitosis phase, they will see that something is wrong, and they will commit apoptosis. This is called translocation. Another one is deletion. We hit one strand and the chromosome never repair itself. So a deletion happened, and it just went wrong and could not divide. Inversion, the two strands got reversed after the hit. You can see here we have the hit. They repaired themselves, but they repaired themselves in such a way that they got reversed. And the damage, like the part that was deleted from here, got itself attached to the top side, and the top side got itself attached to the bottom side. So inversion happened, and again now it is this, the cells of this chromosome are not fit. The cells that are here are not fit to repair themselves, and they will commit apoptosis. Sorry, chromosome is in a cell, so this cell will not divide itself. Then isochromosome, we divide it such that the chromosomes just divide into two pieces, and the chromosomes cannot attach themselves back, cannot repair themselves, and they just die, the cell dies. And then we can have ring insertion and derivative uh, aberrations in chromosomes. So these aberrations, you can see in all these aberrations, when multiple chromosomes got hit, the hits were not lethal, but when they tried to repair themselves, the repair happened in a wrong way. And that repair, when it happened in a wrong way, made the cell to go into apoptosis. And that was multiple cell killing. And this multiple cell killing depends on square of the dose. So according to our graph, this portion is square of the dose, and this portion is dose. So now remember this concept also, square of the dose, because we need multiple events to kill a cell, and dose, direct dose, which where we need single event to kill a cell. So in this equation that we just looked at, this is derived from the Poisson statistics, Poisson equation. I have not touched that equation in detail here. For those of you who are interested in mathematics, um, uh, we can discuss it sometime later, if everyone wants and Asad agrees. Or for yourself, please look at Poisson equation, Poisson distribution. In Poisson distribution, you will see how this equation is derived. When alpha d is equal to beta d square, or if you rewrite this equation, we get D is equal to alpha by beta. Now, this is a very important concept. Then the components of cell kill, sorry here, s- uh, s- let me do one thing here, just move this graph a little higher. Okay. So when D is equal to alpha by beta, then the components of cell killing that are proportional to dose and square of dose are equal. So the components of cell killing that are in the dose region and the components of cell killing that are in the square of the dose region are equal when D is equal to alpha by beta. And if you look here, this is our survival curve. So if we extend the initial curve and we look at its relationship when, and we think of an extrapolated line here, when this dose becomes equal to this dose, we say that this is the ratio of alpha by beta. So theoretically, and this is very important concept here that we utilize during our treatments a lot. So theoretically, when the cell killing because of initial curve and the cell killing because of the later part of the curve, or single hit cell killing and the double hit cell killing becomes equal, mathematically it becomes alpha by beta, and that means we are damaging the cell at the most. We are giving it the maximum dose that we can, and beyond that dose, that will be overkill. So at that dose, that means we can sufficiently killing the cells, and our aim is killing the cancerous cells. We are giving it a sufficient harm. So that gives us the concept of alpha by beta. And for again, in the question answer session, we can talk about it more. But remember, this is a very important concept for our treatments. Alpha is a constant that shows the initial slope of the survival curve. So alpha will be the initial slope, and beta is the constant which will be smaller in magnitude, and that's why alpha beta will always be greater than 1. um, Describing the quadratic component. So beta is describing the quadratic component here. S is a fraction of the cells surviving a dose D. So S on the curve is the fraction of cell that have survived the dose. So the ratio again, I've touched alpha beta again, and I'm talking about it a lot because this is an important concept. The ratio of alpha by beta gives the dose at which the linear and quadratic components of cell killings are equal. That means the components of cell killing that are proportional to dose and the square of the dose. Square of the dose and dose are equal. Or this is the dose where cell killing because of single hit and cell killing because of multiple hits are equal. So as I said, cell killing in the multiple hit area and cell killing in the single hit area becomes equal, and that means we are damaging it at the most. So for example, in this graph, it will be 8 gray. At 8 gray, we are creating an equal effect of dose and square of the dose, alpha and beta. So after cell survival curves, another type of curve that are important to us are dose response curves. A plot of tissue response against the dose is dose response curve. So on one side, we plot tissue response, and on the other side, on x-axis, we plot dose. So a plot will be called dose response curve. So dose response, the result can be clonogenic endpoints, like the cells have completely died, they cannot reproduce, or functional endpoints, the cells have died and they cannot perform the function that they were meant to. So it depends on what kind of cells we are talking about. If they are clonogenic, like they can create colonies and they cannot create colonies anymore, or if some cells are performing some specific function and they are not able to perform that function anymore, that will be the response of dose. That means dose has killed them. After an initial threshold, and we are talking about this curve and this initial threshold, again, this is the concept in radiotherapy that we treat when we treat a patient, say to 200 centigrade a day. We hope and we pray that the normal cells will repair themselves. They will give us a threshold, and the cancerous cells will be kind of in the same stage where we hit them. So when the patient comes the next day, we are hitting the cancerous cells and damaging them more, whereas the normal cells have repaired themselves. They use this threshold concept, and when we are giving radiation again, the normal cells are kind of getting an initial damage. So after an initial threshold dose, after an initial threshold where we see no effect, um, as the dose increases, so does the effect. So as the dose is increasing, the effect is also increasing. Once the maximum effect is achieved, once we have the maximum effect on that organ or on that tissue, a saturation point is reached and the curve flattens out. So we reach to a saturation point. So any dose after the saturation point will not do any damage because we have reached the maximum damage to the tissue. So there is no use to overkill. We can just kill the cancerous tissues to a dose where we will have maximum effect. And beyond that, even we give radiation, we are not doing anything. There are different concepts about dose response curves and different uh, curves. So here we have if you look at the curve A, this is no threshold. So as soon as the radiation starts, the effect starts. We don't have any threshold dose, and the effect starts immediately, and it keeps growing with dose. B, if you look at a curve B, um, A is linear. A is a linear response. B is again a linear response. But B is giving us some threshold area. So there is a dose where we don't see any effect, and then at dose D1 we start seeing effect, and with increase in dose the effect increases. This is again a linear. This is following a linear equation. C, we see no threshold. We start getting damage, but it's a linear quadratic, stochastic, like carcinogenic. So we say that we don't have a threshold. The effect starts, but at the beginning the effect is small, and as the dose increases, so does the effect. The effect will increase with the increasing dose, and then it increases sharply. D, again, when we look at D, no threshold, it's a linear response, but after some incident. That means when there was no incident, there was no dose, everything was fine. But as soon as the incident happened, for example, for somehow a whole body exposure, or someone like if some patient takes radioactive iodine that is going to thyroid. So when that happens, then the effect starts happening. So again, we don't have a threshold, but in the beginning we don't have an effect because nothing has happened, and as soon as some event happened, the effect started increasing. And now when we looked at curve E, we have a threshold, and then in the beginning we do deliver radiation, but nothing is happening. But as we reach beyond a certain threshold dose, the effects start happening, and it's a sigmoid curve. And this is the type of curve that we exploit in our radiation treatments. And this is deterministic effect. So remember, deterministic effects have a threshold dose. We believe that below a certain level of dose, nothing happens. And after a certain level of dose, cells start dying. So again, when we talk about dose response curves, tissue can respond early to exposure. Early responding tissues like skin, mucosa, intestinal epithelium, or there can be late responding tissues like spinal cord. For late responding tissues, the survival curves are more curved than early responding tissues. For early effect, here in the background, if you can see, we have the this B curve is a late responding tissue. So for late responding tissues, the survival curve are more curved. They are kind of this. And for early responding tissues, the survival curves are more straight. So that means late responding tissues have a bigger shoulder here, or DQ dose, quasi threshold dose. That's why they are responding late. For early effects, again, we are talking about alpha beta. The ratio alpha beta is large. For late effects, it is small. For early effects, alpha dominates at low doses. For late effects, beta has an influence at doses which will be lower than early